there's something very important for you to sort of get in your mind and start wrapping into the logic of the class very early in the sequence. And what it is in particular are 3 equations that will be used probably almost with every lesson and every concept in the class from here to the very end of the quarter. 3 equations. I'd like to tell you about what they are in this video here. So what physics is mostly about, at least in this class here, is about motion. That might have been mentioned in another video. And the study of motion here is called mechanics. Probably because studying motion is the nuts and bolts of physics. You certainly need to understand about how motion works and some basic things about everyday objects before you can go into more esoteric areas of physics. So the mechanics and the motion are where we start. So what we have here is to say we have a ball. Now it could also be a car, or a helicopter, or a rock or something, but I'll just draw a ball because they're nice and round and easy to do. And I'll say that the ball is actually located by its center point right there, and it's doing something flying through space. So it turns out that whenever something moves like that, there's always 3 variables that can be attached to its motion. One is x, which is its position. The other is v, that's its speed. And the last is a, its acceleration. It turns out these 3 variables here are the most important ones in all of physics to understand how something moves and where it's going to move, and to just start tying in and using the machinery of physics and predicting motion and learning about motion. These 3 variables just play a really key role. So it turns out then that the way these variables are related are as follows here. The position here has an equation which looks like this. X is x0 plus v0 delta t plus 1/2 a delta t squared. Very long equation, but it's one of the first 3 that you have to get to know, so I would immediately start committing this to memory or just start working out the logic or seeing how the equation works. The other one is v0 plus a delta t. These are 2 of the 3 equations. I'm going to give you a third one in just a second here. But before I give you the third one here, let's just describe what we have here. So it turns out when I'm looking at the ball in the position it's at, just sitting here like this, the x and the v are sort of known as the current or initial position of the ball. I like current better than initial because initial always implies the problem is just starting, but in fact the ball could have been way over here. This could be, say, 1 hour into its motion or something like that. But in either case, the current position, the variables are always subscripted with a little naught right here, a little 0 right here. So I'm pronouncing it N-O-T, naught. So instead of just writing x or v and a, I'm going to write x naught, v naught, and a. A usually doesn't have a naught because of some restrictions of the class. We always deal with problems that have a constant acceleration in a particular situation. So a isn't going to have a naught onto it, but it's an x naught and a v naught. And again, these naughts here always refer to the current or initial configuration of the ball. So the naughts refer to where the ball is right now, where you can see it right now. So if you look very carefully what these equations give you, they certainly have the naughts in there. There's an x naught, and there's a v naught, and there's another v naught right there. And what they tell you then, they say, hey, if you know the x naught and the v naught, this parameter, this one, and this one right here, and you can do some calculations, I will tell you where the new x and the new v are going to be. And that's the predictive nature of these equations. That's why they're so important. In other words, what happens then is the ball's doing something, say it's flying through the air. I have no idea what it might be doing, but sometime later it's going to be over here. And by that time now, that's an important thing which isn't so fundamental about motion because time just keeps going on no matter what. But what I mean by this dotted line here is we let a little bit of time go by, some delta t, maybe a couple seconds or a minute or a half hour or something like that, but we let a bit of time go by and we see the delta t in these side of the equations also. So not only do we need to know the current position of the ball, the x naught and the v naught, but we also have to know how much time did you want to go by. There's a delta t right there, there's a delta t right there, there's another delta t that's squared over there. So if you know how much time goes by and you know the current position of the ball, you're getting closer now to being able to completely compute the new x and v of the ball. So what that means is when the ball is moved all the way over to this new position over here, it's going to have a new position, a new velocity, and likely the same acceleration, which as we'll see can change as problems go on, but for now we'll just say it'll have the same acceleration. I am not going to put a naught next to these variables because it's no longer the current position of the ball, it's the new position of the ball. The ball has gone from here to here, and notice how nicely these equations do in predicting that. Once again, if you know the current position of the ball via these parameters here, here, and here, and you know how delta t, how long you want to wait in time, and lastly, if you know the acceleration on the ball, that last parameter, if you know the acceleration there and there, if you know those 3 things, that will 100% completely satisfy that side of those 2 equations and allow you to come up with a simple answer, a computation for the new position and the new speed of the ball. So these equations are so important that we're just going to call this equation right here equation 1. So we can refer to it in class or in lectures or other things as equation 1. This one here we'll call equation 2. And the last one comes out if we eliminate delta t between the two, which we're not going to do here, but we'll get v naught squared. V squared is v naught squared plus 2a times delta x. So this equation does not involve time. It's very useful and convenient in a variety of situations, as we'll see, but we'll call this equation 3 now. So that's what I mean by having 3 equations in physics, which bring you from the initial or current state of something's motion to its state or position later in time. All 3 of these equations allow you to predict that. This tells you the new position, this tells you the new speed, and this also tells you the new speed. There's some squares, but you can solve for squares here. It tells you the new speed without having to know anything about that delta t. You just have to know how far the ball went, some delta x. So those are the 3 equations which are going to be extremely important in this class, and you should immediately somehow commit those to memory or just know or have those, because the sooner you can sort of get them out, write them out, and use them, the better off you're going to be. And lastly, I just wanted to say that there's nothing particularly sacred about the x-coordinate. In fact, the y-coordinate plays a big role in this class as well. So there's an identical set of equations, only that deal in the y-coordinate. Y is y naught plus v0 delta t plus 1/2 a delta t squared for y. Exact same form, but a lot of the x's have been transformed into y's. And v is v naught plus a times delta t. Another equation there. And v squared is v naught squared plus 2a, and it won't be a delta x now, it's going to be a delta y. But once again, we see the same form of the equations, equation 1, equation 2, and equation 3. Extremely important to start to get to know and be familiar with in this class. But now, as long as we're going to a different coordinate like that, we will be a little bit more careful now, because some are x's and some are y's. And so this equation is pretty clear. There's an x and an x naught. And the v naught here is not just any v naught, but it's an initial v naught along the x-axis. And the a here is an NEA, but it's an x acceleration. Likewise down here, this is not v naught, but v naught x, and a here is ax. So you have that. Here too, this will be vx squared, this will be v naught x, and that will be an ax in there, just to be totally clear about the variables. Physics and math are very famous branches of science for not only drawing variables, but subscripting them all over the place, to be very clear about all the bookkeeping. And the same thing is going to happen here. This is going to be a v naught y, this is going to be an ay, this is going to be a vy and a v naught y in there. This will be an ay as well. This will be a v squared y, and that'll be a v naught squared y, and this will be an ay in here. So what it sort of tells you is that x accelerations affect x motion and y accelerations affect y motion, but there's no crossing between them. Like you don't see a sub y anywhere up here, you don't see a sub x anywhere down here. Lastly, I just want to tie this to something that you probably already know, but we want you to sort of start forgetting it. As you sort of enter this phase of your education here, you've taken things like the SAT and you've done a lot of math word problems, and one of these motion equations, which probably got you quite far, was this one that says distance equals rate times time. And everyone knows what this means. Rate is the speed, t is the time. So if you drive, say, 55 miles per hour for 2 hours, 55 times 2 is 110, you've gone 110 miles. Is that a new physics equation? Is it related to any of these? This is a physics equation, but it's terribly unsophisticated. It is a quickie to remember to get you through some of those tests. We'd probably prefer that you just sort of forget this thing as quickly as you can. Do not jot it down in a pinch or in a hurry, but just recognize that it's up here in equation 2 or in equation 1, all right. Equation 1 is x naught plus v0 delta t plus 1/2 a times delta t squared. You've got it in here. Where is distance equal to rate times time? Well, this equation implies then that the current position of the object is at 0, so this term is going to 0. And it also implies that there's no acceleration in the x direction, so this is going to be 0 too. So if both of those terms are 0, you get that x is v naught times delta t. You can put a circle on that. There is your distance equals to rate times time. So you have that in there. But where this equation fails then, the one that you're used to dealing with here, this doesn't account for an object that has a non-zero starting point, because again, x naught is implied to be 0, and this equation is completely invalid if the object is accelerating. So if the object has some acceleration, meaning its speed is increasing or decreasing as time goes by, this equation is not valid, and you'll simply get wrong answers for that because you're not using it right. So again, I would dispense with the SAT and high school word problem, distance equals rate times time. Just get rid of it from your mind. It is buried inside one of the more useful equations, inside equation 1 there. But if you start to get your mind trained on these are the ones that allow you to make correct physics predictions under any scenario that we could possibly throw at you. Non-zero starting points, non-zero accelerations, and so on and so forth. So there you go, 3 equations. Very important to get to know these and just commit them to memory or just have them available somehow just as quickly as possible.